Hello everyone, this is Puya. In this video I'm going to talk about a new category of sorting called linear sorting. So far in this course and in your previous courses you've seen different algorithms for sorting, including bubble sort, selection sort, insertion sort, merge sort, quick sort, and heap sort. These methods follow different algorithms, like as an example, merge sort and quick sort, they follow divide and conquer algorithm, while heap sort use like a transform and conquer algorithm. Some of them are easier to code than the others, some of them are in place, some of them like need auxiliary memory, some of them are faster than the others, they have different big O notation for worst case, average case, and have like different best case time complexities, and their auxiliary space is also like the needed auxiliary space is also different for each code. Having said all these differences, there is one thing common among all of these 6 different methods that we have seen so far: bubble sort, selection sort, insertion sort, merge sort, quick sort, heap sort. And we haven't seen shell sort, but shell sort is in that category as well. All of these methods are based on comparison, right? All these algorithms are done by comparing different elements of the array or vector and swapping them around, right? Or moving them around, like shuffling them around. So for comparison-based algorithms, any of them can be represented as a binary decision tree. So what is a binary decision tree? So like you can see that it's a binary tree. In this case, for a sorted binary decision tree, sorting binary decision tree, each node represents a set of possible orderings consistent with all the comparisons that have been made, and each edge is the result of the comparison, and the comparison is either less than equal or greater than equal. So for example, here if you have 3 elements in our array, or if you want to sort 3 elements, like in the beginning, these are the 6 different scenarios that we can have, right? Now if this edge represents the result of like a less than b, if we know that a is less than b, then the possible scenarios would be only this 3, and then all the way we can go all the way to the final result, right? So sorting binary decision tree represent the comparisons made by a sorting algorithm on an input of a given size, models all possible execution traces, controls the data movement, and other operations are ignored. So we don't care like how we get from here to here, like how many loops, or like how many helper variables are used. Like we just like model or control the data movement, and it counts only the comparisons. So here you see the decision tree for comparing 3 different elements. This is like a similar decision tree which models uh, insertion sort applied on an array of 3 elements. Okay, and the same insertion sort is modeled for like when it's applied on an array of like 4 elements in this decision tree. So you can see like what happens if like we compare a1 and a2, a2 and 3, like assuming that like the index starts from 1 in this case. Okay, so that's what comparison based sorting decision tree is. Any comparison based sorting process can be represented as a binary decision tree, as we saw earlier. Each node represents a set of possible orderings consistent with all the comparisons that have been made previously, and each edge is the result of the comparison. So in this binary decision tree leaves are the sorted arrays, like the different version of sorted arrays that we can have. So you can see that here, like these are different scenarios that we can have for the sorted array. The same thing for this one, the same thing for this one. The decision tree has n factorial leaves, right? That's the number of permutation that we can have for n elements. You should be familiar with this concept from your discrete math course. Now, the height of the tree, the height of this decision tree is the number of comparisons that are executed for a given permutation of the sorted values. Therefore, the height of the tree is the running time of algorithm. So each edge that we pass, right, is a comparison that we make, right? So the height of the tree, which is the length of the length of the path from the root to the deepest leaf, that represents the worst case runtime of the sorting algorithms. It basically tells us like how many comparisons we have to make in the worst case to get from the initial array to the sorted array. So what is the minimal height for a tree of n factorial leaves? So we want to know, like we want to find a lower bound for the number of comparisons that we have to make to get from an initial array to a sorted array. We want to find like what is the minimal height, what is the lower bound, what is the lower limit to just basically sort the array. A binary tree of height h can contain no more than 2 raised to power h leaves. We saw that in the previous videos on trees, right? And so if we follow these computations, right? So like, and we just like know that like the height can be the height of the tree, like minimum can be log of n in base 2, right? And we follow the same computation that's done here, and we get to this final result that to sort n elements, comparison sort must make n log n comparisons in the worst case, right? So that basically shows that the previous sorting algorithms that we saw earlier, heap sort and merge sort, are asymptotically optimal comparison sorts, right? We can't get to a asymptotic notation which is like smaller than n log n, right, for sorting, if our sorting algorithm is based on comparison. Okay. So more precisely, there exists a bad input for that algorithm on which it takes n log n comparisons, like order of n log n comparisons, to get from the root to the deepest leaf. And this theorem can be extended for the average running time as well. Okay. Now, what if we are very eager to find a sorting algorithm which is faster than n log n? Is that possible? Yes. So we have a different category of sorting algorithms that can be applied in certain cases for certain scenarios called linear time sorting. So most sorting algorithms rely on comparison between two items, proven to be in the order of n log n. Can we do better? Can we do like order of n linear time algorithm? We can if the input has a special structure. For example, uniformly distributed, right? Or like every number can be represented by like a limited number of digits. And we'll see like what these requirements are, like when we talk about counting sort and bucket sort. In that case, we can beat the n log n running time if we use other operations than comparing elements with each other. So you can think of the process that you follow when you want to sort a deck of cards. Like one process of doing that would be keeping a pile for each value from ace to king and put all the cards with the same value in the same pile and then sort them based on their suit, right? But since there are only 4 cards per pile, right, this will be done in constant time, because like our order of time complexity would be a constant, right? So like you can finish this in linear time, because each pile that we had only we only have 4 suits in a deck of cards, right? So like each pile would only have like 4 cards. So like we could finish this in linear time, like if we have like the whole deck of cards and we want to sort it. With more information or assumptions about the input, we can do better than comparison sorting. So consider sorting integers or real numbers. Additional information or assumptions that we might need to apply linear sorting would be, for example, if we know that the integer numbers in a certain range, if we have that information, then we can apply linear sorting. Or if we have real numbers in the range between 0 to 1 and we know that the numbers are distributed uniformly. We'll talk about this condition in more detail later. So in these cases we can apply linear time sorting. The 3 algorithms that we see in this lecture are counting sort, bucket sort, and Radix sort. This picture summarizes like some of the sorting algorithms that we have seen so far, right? So like most of the algorithms that we have seen so far, or all of the algorithms that we have seen so far, are comparison-based sorting algorithms. Now we're going to talk about linear time sorting algorithms, counting sort, bucket sort, and Radix sort. So let's first start with the counting sort. So assume that we have n integer numbers in the range 0 to k, where k is an integer and k is of order n. Okay, we'll see that like this also applies on characters as well, but like now let's just focus on integers. So counting sort works by first counting the occurrences or the frequencies of each data value. So each of the data values that we have that are in the range between 0 to k, we count how many times they occur in the array. So like we calculate their frequency. And then determine for each input element x its rank. What is the rank in this concept? It's the number of elements less than or equal x, right? So for example, the rank of element 4 would be all the number of elements in the array that are smaller than or equal 4. Once we know the rank of x, we can place it in the appropriate position, right? So like if we know that there are maximum 4 elements, there are like r elements smaller than or equal x, then we know like where x is supposed to go, right? So because we know that like these are there are r numbers that are smaller than or equal x, right? So the latest or the furthest position for x would be at location r minus 1 if the index starts from 0, or it would be at the location r if the index starts from 1, right? Because we know that there are only r numbers that are smaller than or equal x. So when it comes to linear sorting, we care about another property of sorting algorithms called stability of the sorting algorithm. So a sorting algorithm is called stable if the relative position of elements with the same value will not change after sorting. So if you have two elements with the same value, before and after sorting, their relative position should not change. If, like, let's say x1 and x2 have the same value, if x1 is before x2, in the sorted version, x1 should come before x2 as well. The counting sort, we don't make any comparisons. So how does it work? So counting sort is a sorting technique based on keys between a specific range. So we know the range. Works by counting the number of objects having distinct key values, then doing some arithmetic to calculate the position of each object in the output sequence. For simplicity, consider data in the range 0 to 9. So let's assume that, like, we have this array, right? And the information that we were given is that all the elements of this array are in this range, right, from 0 to 9. So first thing we do, we create another array, like an auxiliary array, right? This is, like, let's call it C, or C for short for count. Okay, so create a count array to store the count of each unique object. So initially the count of all elements is 0. You can see that here, like, before we start going through this array, the count of every element is 0. Count each element in the given array and place the count at the appropriate index. So what we do here, like, if this is our array, right, so like you see that, okay, like this is 1, so this is going to be incremented. 4 is going to be incremented. 1, this becomes 2. We have a 2 here, this becomes 1. We have a 7 here, this becomes 1. We have a 5 here, this becomes 1. We have a 2 here, was 1 already, and now becomes 2. So we end up with this count array. Okay, so this count array now shows, like, the frequency of each number in the array, right, or each index in the array. Okay, now what we are going to do now, we modify this count array. How? So, like, instead of, like, showing the frequency of each number, right, we say, like, how many numbers, how many elements are smaller than or equal 1. How do we do that? By starting from here, starting from index 1, and adding the adjacent element to the next element. So, like, here, like, 0 plus 2 becomes 2. So it shows that there are 2 elements in the array that are smaller than or equal 1. Then we add 2 plus 2 becomes 4, right? So, like, now we know that, like, there are 4 elements in the array that are smaller than or equal to 4 plus 0, right? This is the same array, we are modifying it. So 4 plus 0 becomes 4, 4 plus 1 becomes 5, 5 plus 1. So now this array, which is the auxiliary array that we have, shows the rank of each element, right? So it shows that for number 1, like, we have 2 elements in the array that are smaller than or equal 1. Okay, so this shows, like, the last position that number 1 can be at, right? Because we know that there are 2 elements in the array that are smaller than or equal 1. So this shows the last position that 1 can be placed at. Right, so based on this one, since we have 7 inputs, we create an array with 7 places. So now that, like, we have modified the count array, now we want to find the output. Since we have 7 inputs, we create an array with 7 places. Corresponding values represent the places in the count array. We place the objects in their correct position and decrease the count by 1. Now let's see what this means. So here like now we have two arrays, like the input array and the count array, right? And we also we want to create the output array. Okay, we want to create the output array. So how is this gonna work, right? So if we create the output array with the same number of elements as our input, now in order to have a stable counting sort, we go from the end of the array from the right side toward the left side. So I find 2, okay, right? I go to index 2, and the rank for number 2 is 4. So it means that there are 4 elements in this array that are smaller than or equal to. Okay, and I'm gonna fill out the array from end to the beginning, right? So like this one, right? I know that there are 4 elements that are smaller than or equal to, right? So I'm gonna place this one at location 4, okay? But location 4 would be index 3, because in C++ our indices start from 0. So this 2, it's gonna go at index 3 of output, right? So like this is like where this 2 is gonna go. Okay, once we do that, because we finished this one, we also gonna decrease this count for this index to 3, right? Because now we know that in the rest of the array, we only have 3 elements that are smaller than or equal to. Okay, so once we moved this element to here, we now decrease the count for this index to 3. Now let's go to the next element, 5. Okay, again I go to the corresponding index of the count array, right? And here it says that for 5 there are 6 elements in the array that are smaller than or equal. Sorry, I should show you this one. That are smaller than or equal 5, right? So what am I gonna do now? Oh, sorry. What am I gonna do now? Right? I know that this 5 can be placed at location 6 if the locations start, if you start counting the locations from 1. But because the indexes start from 0, means that this 5 can go at index 5, like 6 minus 1. And then once I did that, once I do the move, I'm going to decrease this count by 1. Next one, 7, right? 7, right? It's its index is 7. It's going to go here, right? So again, we have 7 elements that are smaller than or equal 7, right? So like this can go at the location at index 6, right? At the 7th place, which is going to be index 6. 2, now I'm going to look at this one. This is 3. So like this is going to go at the 3rd place, which is going to be index 2. 1, I'm going to look at here, right? The rank of it is 2. It's going to be placed at the 2nd location. Once we move it, we're also going to decrease this to 1. 4, it's at the 5th rank, right? So it has to be at the 5th location, which is going to be index 4. And finally 1, I'm going to look at it. Now this was decreased to 1. So this is going to be at the 1st place, or the index 0. So this is the whole concept of counting sort. You see that we have 2 auxiliary arrays, like 2 auxiliary memory spaces, one for counting, right, and finding the frequency of elements and then finding the rank of them, and then one for output. Once we do that, we can copy back all the elements of the output array into the input array. Okay, This is the algorithm to implement counting sort. So here let's assume that we have n elements in the range from 0 to k. Okay, from 0 to k. So first thing we have to do, we have to create this count array. So we have a count array and we initialize it with 0, right? Then we count, like we find the frequency of every element in the array, right? So like here, like if this is 1, this is going to be incremented. 4, this is going to be incremented. 2, this is going to be incremented. That's like what is implemented here. Okay, so at this point, Ci contains the number of elements equal to I, but then we want to find the rank of them. So like we want to find like the number of elements smaller than or equal I. So what we do, we just like basically starting from 1, starting from the second location, we start adding the adjacent elements, right? So like basically adding like if you start from here, 0 plus 2 goes here, 2 plus 2, 4, 4 plus 0, 4, 4 plus 1, 5, 5 plus 1, 6, 6 plus 0, 6, and so on. So once we found the, excuse me, the rank of each element, now what we're gonna do, right, we have to fill out our output array. So like here, this B is our output array, okay? We like for we go backwards from like we look at the array A, but we go from end of it to the beginning. I'll mention why this is the case like in a minute. Like so, but we go from end of it to the beginning, right? And what we do, we just basically find the rank, right? But because this gives us the location and our indices start from 0, so we have to like subtract this by 1. So we move AJ to this location in B, and we also decrement the element in the count array. So if we follow this algorithm or this pseudocode, see that the overall time it's going to be in the order of n plus k. Okay, n plus k. Right, so if k is a constant, then this is going to be in the order of n. Right, it's going to be in the order of n. And if k is like smaller than n, it's constant, like this is going to be in the order of n. Right, so you see that like we have 4 loops here, like it's going to be basically 2n plus 2k, and that's why like this is the order of n plus k. Now the reason we go backwards when we want to fill out the output array is that we want to make sure that counting sort is a stable sorting algorithm, right? So like here, if I name this one 2a and this one 2b, I want to make sure that 2a comes before 2b in the sorted version. If this is 1a and this is 1b, I want to make sure that 1a comes before 1b in the sorted version. Okay, that's the stability property of sorting. Okay, in order to make sure that our counting sort is stable, we go from end to the beginning, right? We can also go from start to the end, but that doesn't satisfy the stability property that we want to have for counting sort. And we want to see why we want to have this counting sort to be stable, because counting sort is going to be used in Radix sort as a subroutine, and Radix sort requires a stable algorithm, right? So that's why like here we go from the end to the beginning. That's why like this goes from index n minus 1 down to index 0. Here like you also like see the implementation of this in C++. Sometimes the range is given, right? So like the k is given. Sometimes like you can calculate it as your maximum, right? So like here, like in this version, we have another loop that finds the maximum, and then the other 4 loops that we saw here, just like to find the, to initialize the count, to then find all the frequency of the elements, to find the rank of them, and then finally filling out the final the output array. And you see that like here we need like auxiliary arrays, so once we are done we also have to deallocate. The running time is order of n plus k. Okay, and we also need extra memory space. Is it an in-place sorting algorithm? It's not in place, right? You saw that like we are like using extra arrays to do the sort. Okay, one of these arrays is the order of k, right, which is here like 9, right? The other one is the order of n. So its auxiliary memory space is also going to be in the order of n plus k. Okay, so this method works like if k is a small number compared to n, right? What if k was n squared, right? What if we wanted to sort 32-bit integers, right? In that case, like the maximum or the range that we have is huge, right? So like in that case, k is basically n squared. Now like our running time is not going to be linear anymore. It's going to be quadratic, right? So this is like the condition to apply counting sort is that we have a limited range of numbers. So like let's see some examples. So starting from this array, right? First we found the frequency of every number, right? 0 is repeated once, 1 once, 2 once, 3 we have 3 2s. We don't have any 4. We don't have, or we only have 1 5, and we have 2 6. Then we just like one, so like we only have like 1 0. Then we have 2 elements that are smaller than or equal 1. We have 2 plus 1 3. We have 3 elements that are smaller than or equal to 3 plus 2 5. 5 plus 0 5. 5 plus 1 6. 6 plus 2 8. So in this case contains all elements less than or equal to the index that we have here. Okay, and then now we start from the end of A and we go backwards, right? So for each element we look at it, right? We look at it, we go to the corresponding index at the count array, right? So this would give us the indication that 0 has to be at the first location of the output array. What is the first location? It would be index 0. So then 0 is going to be placed here. Once we move the element from A to B, we're also going to decrease this count by 1. So this becomes 0. Let's go to the next one. Here, 6, right? So 0, 1, 2, 3, 4, 5, 6. Am I right? Yes, this is like index 6, right? We come here, right? So like for 6, this shows that it should be at the location 6, right? It should be at the location 6, right? So it basically shows that there are 6 elements that are smaller than or equal 0, 1, 2, 3, 4, 5, 6. Sorry, I'm here. Not this is C6. Okay, I'm sorry about that. So it basically shows that for here, like I get here, like so like this is 6 and C of 6 is 8. So it basically shows that there are 8 elements in A that are smaller than or equal 6, right? So I'm gonna put the 6 at the end of all those elements, right? So like the latest position the latest location that 6 can go would be at the location 8, which is gonna be index 7, right? So we're gonna place 6 at the end here, and then we are gonna decrement this one, this index to 7, as you can see here. And this goes on, like for 5, right? 0, 1, 2, 3, 4, 5, right? This one, right? So like it shows that it can be, there are this 5, there are 6 elements that are smaller than or equal 5, so like 5 can be placed the latest at the 6th location, which is going to be index 5, so that's where 5 goes, and this continues, like, so we go backwards. Since we start from the last index of A, this results in a stable sort with the big O notation of n plus k. Notice that we didn't compare any of the elements, right? We didn't make any comparison between elements. You see another example here, right? So like for all of these, we have an input, all of these 3 examples, we have like an input array, we create the rank, and based on that, like we fill out the output array. Okay, so like something to notice that when there are no repetitions and n is smaller than k, so here like we have 4 elements, but like n is 4 but k is 5. So in this case some cells are unused but the indexing still works, right? So like you see that this counting sort works even if n is smaller than k. We have 4 elements and but like they are the range is larger than n, k is larger than n. Okay, so let's look at this one again. So this is our count, the frequency. First of all, this is the frequency array, and then we modify the count, right, to find the rank. We start from here, 3. Okay, it has to be at location 7, which is going to be index 6, so 3 is going to move here, right? And what we are going to do, we're going to decrease this one to 6, right? So after we move 3 here, this is going to change to 6. 0, like we go here to index 0, this should be at the 2nd location, which is going to be index 1. And once we do that, we decrease the count, so this becomes 1. Then 3, this goes here, and this continues. So like I didn't show the full process, we only filled out the 3 elements, but this continues all the way to index 0 of A. Okay, so like here, like it's a review of stable sorting algorithms. A sorting algorithm is stable if for any 2 indices I and j with I smaller than j, if ai is equal to aj, elements ai precedes element aj in the output sequence, right? So basically it tells us that like for a stable sorting algorithm, relative position of 2 equal elements remain the same after sorting, right? Like it means like if they are like if one of them is preceding the other one, like in the sorted version also like going to be preceding the other one. So here like you see that we have 2 2's, right? Let's call this one 2 1 and this one 2 2. In the sorted one, 2 1 comes before 2 2, right? Okay, we only have 1 7, but we have 2 4's, right? If this is 4a 4b, 4a comes before 4b. Okay, and the same thing for other elements. So stability property of counting sort will be used in designing a new sorting algorithm called Radix sort. Okay, and counting sort is stable. So the next algorithm we want to see is bucket sort. So in this algorithm, we assume that all the elements are distributed evenly in a known range of values. even distribution or uniform distribution means that any two equal size subranges contain roughly the same number of real numbers in the list. But this subrange, it means like these buckets. So like if we have like different buckets, like we want to have almost the same number of elements in each of them, right? We want to have like an even distribution, a uniform distribution among these buckets. We can set up k buckets, each responsible for an interval. So like this, yeah. So like if we have should be n buckets. Sorry, if like this should be n buckets. Or if I want to make this one like k, that's what would be good. Sorry about that. So if we have n numbers, right, we set up k buckets, so each should be responsible for an interval of n over k numbers. If we can easily match a value to its bucket, then we will be able to place all the elements in their buckets in linear time. Okay, we'll see like what this statement means through examples. Elements are usually keys paired with other data. So like we have some comparable object, so that we're not going to compare elements, but like they have like each element has a key. With uniformly distributed keys, the expected number of items per bucket is 1. The sorting or like it's going to be constant. The sorting each bucket takes order of 1. And so like, and we only have n buckets, and the buckets will be sorted, so it's going to be just like easy to concatenate them. And so ideally, if all these assumptions are valid, then we can sort an array using bucket sort in the order of n. The total effort of bucketing, sorting buckets, and concatenating the sorting buckets together is going to be order of n. So what we're going to do, we want to put each element in the correct bucket, sort each bucket, and then concatenate the buckets, meaning like putting them right after each other, putting each element in the bucket, and concatenating the buckets will take linear time. And sorting each bucket depends on the number of elements mapped to each bucket. So basically what this whole thing means, I know this is very vague, but like it means that like if we have a bunch of numbers, right, we're gonna assign different buckets, right? So here, for example, like the bucket is the digit itself, like 1, 2, or 3. We're gonna put 1s here, 2s here, and 3s here, right? The buckets themselves are sorted, right? Because like that's how we define them, right? So what we're gonna do, we're gonna sort the elements inside each bucket, right? So ideally, like if we have uniform distribution, we have like a very small number of elements in each bucket, ideally 1. It's going to be order of 1, right? So it's not going to take that much to sort what is inside the bucket. When that's done for all the buckets, we're going to just concatenate all the elements inside the buckets right after each other. So that's the whole concept of bucket sort. So you see here how this concept is applied to sorting this array of double numbers, right? So like this array, like it comes in the range from 0 to 1, right? So then we have like 10 different buckets, right? You see like here, like we have another array that represents the bucket. Okay, so what we're gonna do, right? So like we basically for each of these, right? So like this like for each of these buckets, the range like here like it would be from 0 to 0.1. For here would be 0.1 to 0.2. For this one would be 0.2 to 0.3. So what happens here, like we go through every element and then we put them in the corresponding bucket. So now like the buckets here can be either empty, right, or like we can have multiple elements in each bucket, right? And each of these buckets we can either implement them using linked list, or we can implement them using queues, right? So once these placements are done, or at the same time that we do the placement, we also like apply sorting for each bucket. But you see that like for each bucket we have a small number of elements. So instead of sorting 10 elements, now we only have to sort 2 elements. So we can apply a sorting algorithm, let's say insertion sort. It can be also quick sort. So we can apply a sorting algorithm for each of these buckets. And once the buckets are sorted, what we are gonna do, we're just gonna concatenate the buckets. So this one goes first, then this one goes next, then this one goes, then this one goes, this one goes, and this one goes. The same idea can be applied to linked lists, right? So like first, like we like put the elements inside the buckets, we sort each bucket, right? So like these can be either linked list, or they can be arrays or queues, like so queue like can be implemented using linked list or array. And so we sort each bucket, and then after that we concatenate buckets. Okay, so let's assume that S is a sequence of n items, right? N items. We have n items with keys in the range 0 to n minus 1. So like here, like we're discussing for integer numbers, we have an array or vector of n elements, right? The range for the numbers is from 0 to n minus 1. Bucket sort uses the keys as indices into an auxiliary array B of sequences. So here like we have this auxiliary array B. Empty sequence S by moving each item into its bucket. So like we first move each item into its bucket, and like once we place them, right, we also like sort them, and then when we are done for I from 0 to n minus 1, move the items of bucket BI to the end of sequence S, right? So what happens here is basically like we are placing the elements in the buckets and sorting them at the same time. Just like putting elements in the buckets, it's going to take order of n. Phase 2 takes order of n plus capital N, which is the range. So like the time complexity of bucket sort is order of n, which is the number of elements in our array, plus the range, right? So like here, like we can call it range or k. So it's going to be order of n plus k, similar to counting sort. The algorithm for it, just like basically we distribute elements over buckets, right? So like what we do, we just like basically like do inserting AI into the list B, right? We for each of these buckets, right, we do sorting. So you see that like here, like we have like different lists. For each bucket we have different number of elements. So for each of these lists we do sorting. What kind of sorting? Insertion sort. So you might ask like, oh, but insertion sort is quadratic, is order of n squared, right? But pay attention that for every bucket we have a small number of elements in it. Ideally, if this is uniformly distributed, if the data is uniformly distributed or evenly distributed, at each bucket we have ideally one element, right? But like nothing is ideal, right? So but like it's going to be a small number of elements in each bucket. So we do insertion sort for each bucket, and then we concatenate all these buckets in order. So here the C++ implementation of bucket sort for like an array of float is given, right? So like here you see that like first create an empty bucket assuming size n, right? So like we have this. Then we just the next step is put array elements in different buckets. So that's what we do here, right? So that's what we do here. Like we just like have like we placing elements in the buckets and then sorting individual buckets, right? So like here we're calling the sorting algorithm, let's say like this is quick sort, so we're calling this sorting algorithm to sort each bucket and then concatenate all the buckets into the array. Okay, so in the worst case scenario, if our data is not uniformly distributed, if all the data is in one element, right, then we have n elements that has to be sorted, then this is going to become order of n squared, right? So like ideally we want to have something like this when the data is distributed uniformly. Running time is order of m plus n when n is the number of elements in the array and m is the bucket number of buckets. In terms of space complexity is going to be the same, and if m is much smaller than n or m is smaller than n, like we're going to reach the linear time complexity. A bucket sort is also stable. If two elements are equal with respect to sorting and they appear in the input in order A, B, then they remain the same order in the output. Okay, so for the running time of the bucket sort, all parts except bucket sorting takes order of n, right? So like you see like we had three different steps, right? Like distribute elements, right? And then concatenation, right? Each of these are like taking like order of n. The only part that is quadratic is the sorting, or like if it's like insertion sort is quadratic, if it's quick sort is n log n, right? But in the worst case, right, all the numbers will end up in the same bucket, so in the worst case it will take order of n squared. Given that the input sequence is drawn uniformly, the expected size of a bucket is order of 1. So in the average case, only a constant number of elements will fall into each bucket. So it will take order of n, right? So like there are proofs in textbooks, in your textbook, that you can see. So like we can also like if we see that our buckets are not uniformly distributed, we can use different mapping methods with different hashing or mapping indexing methods. Now that you've seen also hashing in your course, like this should make sense, right? So we can use like a different formula basically to map the elements into buckets or transform the elements into bucket. Bucket sort takes linear average case time for uniformly distributed numbers. Okay, we'll see like some examples for bucket sort, like more examples for bucket sort when we talk about Radix sort. So the next concept is Radix sort. So Radix is the same as base. In decimal system, Radix is 10. Example, the following is a decimal number with 4 digits. So if we have a number with 4 digits, if we have n numbers with 4 digits, suppose we are given n d-digit decimal integers, right? We have, let's say, like n numbers with 4 digits, Radix sort tries to do the following. So like it basically starts sorting, right, sorting the elements digit by digit, either from the least significant digit to the most significant digit, which is the Radix sort you're gonna see in this course. It's called LSD, least significant digit Radix sort. So we start like by ignoring digits up to the digit that we have. Like we only like sort the elements one digit at a time, and then we go to the next one, and then we go to the next one, right? How do we sort the elements based on just one digit? We either can use counting sort or we can use bucket sort. Okay, and the reason like we wanted to make sure that counting sort and bucket sort are stable was because like we're going to implement them in Radix sort. So there are two different meanings for Radix. So according to the dictionary, is the base of a number system, but the alternate terminology is that Radix is the number of bits needed to represent 0 to base minus 1. Okay, so what does that mean? It means like, for example, for base 8, right, we have to represent, so the number of for base 8 we need Radix 3. We need like the number of bits, like let's say like you wanna represent numbers from 0 to 7, right? 0 to 7. 7 needs 3 ones, 3 bits, right? So we can say that it's Radix 3. Okay, so this is the alternative terminology, like alternative definition. Like in this concept of Radix sort, it mostly has the same meaning as a base. It was first used in the 1890, right? In the US census. So like it's a pretty old algorithm, but still like it's like efficient for some scenarios. Like it's also like was used like in punch card sorters. So like when computers like had punch cards, like this sorting algorithm was used. So in the Radix sort, assumption is that all elements are represented by the same number of digits and are of a known range. Okay, so all elements are represented by the same number of digits and are of a known range. We sort from least significant to most significant digit using a stable sort each time. Okay, so like this is called LST Radix sort. There is also MSD Radix sort, but like in this lecture we're gonna see like we start sorting from least significant to most significant digit. Usually you use either counting sort or bucket sort for each digit, and this method is not comparison based. Radix sorting mirrors a real life approach to sorting. Given a selection of books, we might first make a pile of all the A author books and all the B author books, then we would sort each pile, right? Or if given a series of 10-digit numbers, we might first sort according to the first digit and then according to the second digit, and etc. So that's basically what the Radix sort is. We use a stable sort for each digit and we go from the least significant digit to the most significant digit. Okay, so let's look at one example, right? So here we have this array, right? So first let's only look at the least significant digit. So we're gonna sort these numbers based on their least significant digit. How are we gonna sort them? These are like integers in a certain range, so we can use either counting sort or count sort or bucket sort. So after like sorting the first digit, right? This is where what we end up at, right? So 0, 5, 6, 7, 7, 9, 9. And let's take a look at here, right? So you see that 329 comes before 839, and 457 comes before 657 in this case. Why is this the case? Because we applied a stable sorting algorithm, right? So the relative position of elements with the same number, it's going to be remained in the output. In the next stage, we're going to apply again either counting sort or bucket sort to the second digit, right? So ignoring the other digits, we're going to apply either counting sort or bucket sort to the second digit, right? So like here, like 720, then 329, right? And then 436, then let's say like we have fives, right? So like we're gonna have 355, 457, and 657. And again, look at it, like the digits that have the same numbers. So like here 720, we have 2 in the middle, and 329, the second digit is 2. 720 comes before 329. The same thing for all the fives, 355, 457, 657, right? So like this order is maintained because of the stability of the sorting algorithm. And then finally we are going to sort them based on their last digit, or the most significant digit, right? So like most significant digits are 3, 4, 6, and 7. So the 3's should go first, but 329 is going to be before 355. And then 4's go next, like 436 and 457, then 657, 720, and then 839. Okay, so this is how the Radix sort works. So one of the main shortcoming of counting sort is that it is useful for small integers, like only like 1 digit or a smaller range, right, where k is very small. But if you have a large number, like we have a array of large numbers, then like we can use Radix sort. So again, like you see an example of Radix sort, and this is the pseudocode for it. Here, like we see another example, like if you have this array, okay. So first of all, you see that the number of digits in each number is different. So like if we have the maximum number of digits is 4, then we're gonna fill out what's missing for the other numbers, like with 0. Okay, so we'll see that like here, like we had 29 here, like we made it 0, 0, 29. So like what we do, we start from the least significant digit. So this is the same original array, but we are looking at it, and then we just like sort them based on the least significant digit, right? So you see that like how this is done, okay. And then it's like I put everything twice, like this was not needed. But then the next stage is looking at the second least significant digit, sort them based on that, right? Then the third one, and then for the fourth one, like we have to place some zeros here, right? And finally the array becomes sorted. So this is the stability, like this happens because of the stability rule, because the counting sort or the bucket sort that we applied for sorting each digit was stable. Okay, this can also be applied for binary numbers, right? So let's say that we have a 4-digit binary number, right? So when we have binary number, our buckets, it's going to be like only 2 buckets, 0 and 1, right? So we have 2 buckets. Or like when we want to count, we only have 2 elements in our counting sort. Okay, so like Here, like this can be also like it's more common to make this K, so let me make it K so that it's consistent with other things that we had for bucket sort and counting sort. Okay, so here you see that like we have bunch of binary numbers. Again, we start from sorting by the least significant bit, right? So you see that like the zeros are going to be first, the ones are going to go next. Then we sort by the um, bit. If this is bit 0, this is going to be bit 1, and then the next one, and the next one, and eventually our array is sorted. Okay, so I mentioned that I'm going to talk about bucket sort like when I talk about count Radix sort. So here you see that again, like we have this original array, the digits, right, can go to either of these buckets, right? We start sorting from the least significant digit, right? You see that here we have buckets, and each bucket can be represented by queues or like linked lists or arrays. So like you see that like here based on that, right, we don't have any zeros, we don't have any ones, we don't have any 2s, 5, 6, and 7, but like these buckets, right, based on bucket sort, right, like these are gonna be sorted, and we're gonna be just like placing them here, right? But because like we're only sorting one element, right, one digit, right, so like the order is only gonna be maintained, right? We are not sorting these three numbers. We are basically sorting these threes, right? But they're the same. So if they're the same, it means like their order is going to be the same. 0, 1, 23, 2, 0, 43, and 1, 7, 7, 3. Okay, so then the concatenate the buckets. So that's what we end up after sorting the least significant digit. And then we're going to sort the second least significant digit, right, again using bucket sort. And then the third one, and finally the last one. So this is like how we end up with the sorted array. Okay, the same concept can be applied for linked list, right? So like we can sort after the just like if you have a range of numbers which are 3 digits, so we can do this like on least significant digit first, right? You see like all the ones are first, and then fours, and then 5, 6, and then second one, and then third one, and this is like how we can sort the array. This shows another example, and here like we are using again bucket sort as the subroutine for Radix sort. So let me mention this. Radix sort can be implemented using counting sort or bucket sort, right? Both of them can be applied. It's more common to do it using counting sort, right, to save more space, right? Because like in the bucket sort, you see that like we end up with lots of either like linked list or like queues, right? So the counting sort is very common for um, implementing Radix sort. Another example, right? So like again, like this is bucket sort, and you see like here like buckets are implemented using linked list, and like once we once we place elements here, like we also sort them as well, and then we end after 3 passes, right? So like we have 3 digits, right? So after 3 passes we're gonna finish, right? So what is the running time of Radix sort? If we have n items and d digits of maximum value k. What does that mean? N items. So here we have 1, 2, 3, 4, 5, 6, 7, 8 numbers. So like here n is 8. D digits. We have, in this case, we have 3 digits. If n each number is a 3-digit number, and maximum value of k, each digit maximum value is 9, right? So like, because our digits are going to be 9. If it was binary, k would be 1, right? So k would be 1. So let me go back to the example that we had, binary elements. So here n is 5 because we have 5 numbers, right? The digit is 4, okay? And then like the range, we only have 2 numbers in our range, right? We have 2 numbers, so like k is like 2, okay? And in this one, like it's better to say like k is 10 because we have 10 distinct values, okay? So how many passes do we need, right? So like we have to do it for every digit, so we have to do it in d passes, right? From the least significant digit to the most significant digit. How much work per pass? So because we are using counting sort or bucket sort, we saw that to do counting sort for n elements in which have the range of k, okay, so like we have like k values, k maximum values in our range, then the time complexity for that is n plus k. We saw that for the Radix sort, for counting sort and bucket sort. So the total time needed, it's going to be d times n plus k. So it's going to be order of d times n plus k. So now if d and k are small compared to n, right? This is going to be almost linear, so not truly linear if k is large. Radix sort is only good for large number of items with relatively small keys, like they come like in small keys, like it means like the range is very small. The storage, Radix sort space complexity is bound to the sort that it uses to sort each digit. In base case, that is the counting sort. It's going to be order of n plus k. A disadvantage of Radix sort is that it requires a large amount of memory to keep all the sublist and the master list at the same time, and it's very hard on the cache. So one thing that you should notice, like if we increase the base, like let's say like if we go to the binary digits, right, in the binary base 2, then in the binary k is going to be only have 2 different values for our digits. It's either 0 or 1, right? So increasing the base r decreases the number of passes but increases the max value of each digit, right? So if we decrease the base, k is gonna be smaller, right? K is gonna be smaller, but we end up with more digits, right? Why? Because let's say like number 8 in base 10 only has 1 digit, but in base 2 would be 1000, so it would have 4 digits. So increasing the base decreases the number of passes but increases the maximum value of each digit. So it's basically compromise. Radix sort is stable. It can be fast if for certain arrays that follow the requirements of Radix sort, and it doesn't sort in place because it uses counting sort or bucket sort. So it's not an in-place sorting algorithm. Okay, thank you so much. That was it for